Okay, perfect. Good morning. My name is Cosimo Iasiello. I am a team leader in geotechnical and tunneling in IESA. IESA is a global consulting. As part of my academic work, I'm also collaborating with the Technical University of Madrid to develop some routines in MIDAS GTS. Okay, the structure of this webinar is regarding the excavation on the water table, which is a really interesting matter, in particular for the soil structure interaction between also. There are some issues that are not clearly related to civil engineer, so like, for example, the hydrogeological and geological conditions. The structure of this webinar is completely open, so if you want to, I'm going to give my my presentation, but if you want to stop me each time you have some doubt or you want to go through the models we are going to share here, just send me in a chat a communication, and I will try. Okay. So I don't know if you can see my my screen. I hope you can see my presentation. The index of the webinar is it's really easy. It's groundwater problems in deep excavation, numerical analysis versus the analytical solutions. I mean, when we should carry out numerical analysis and when we can solve the problem with analytical solution. This will be analyzed further in the presentation. Then I bring here some case studies in GTS and also some trick we can use in MIDAS to sort it out some problems that are not related, some problems with the numerical calculation more than with the and then we can have conclusions. Okay. Okay, so I will regarding groundwater problems in deep excavation. I'm just this is very go very quick. I mean, everyone knows I'm sure everyone knows in this webinar with the problem with the water. If this is our excavation, and here we have our level of props. And here we have the pressure of acting on the structure. This is affecting directly the effective stress in active and passive conditions. So when we are going to design a structure or an embedded wall in underground groundwater, is important to evaluate both conditions. I mean, the increment of our pressure, active pressure onto the structure, and the disequilibrium we are going to have on our passive. Okay, starting for some construction advice when we are going to work with, for example, an embedded wall with anchor bars. We have to provide this sort of details in order not to have this problem. This is the problem you can face when you are excavating and water. Okay, this as you can see here is the water, the anchorage. We already have this forest. There is no excavating without under the water table, and here we are taking time to inject the ground so water has the possibility across this green table, which is pipe. So across this green pipe, extracted ground to can stop the coming of coming back to the presentation. So this is anchors with the possibility of grouting. And so we will here we have an hotel, and this hotel we could stop the coming of water. Okay. Another problem of the excavation of for example, of a embedded wall is the so-called suppression. I mean, the pressure acting of the base slab. This is a case of a tank close to a river. I mean, based on my experience, we have three possibilities regarding the suppression. Live with the suppression, the watering. I mean, carrying out the watering permanent with permanent, or carrying out some sort of soil treatment. For example, in this case, it was carry out columns of jet grouting. And also in this case, we can use our jet grouting as an additional weight to calculate our uplift or heave, depending if we are in clay or in the sand, to contrast the acting force on water. Also, some standards, in particularly the Italian, but also in the Spanish, there are some references regarding the considering the jet grouting as with some defects. So here, the area of the jet grouting should not be considered like it is in this A, but should be considered a bit less. This also can be done in our numerical analysis. No. Now, taking out not to do so much noisy here. This is a video regarding the suppression. Here was done some columns. Here is the base slab. Then was perforating the base slab to check the flow under the flow under the base slab, and you see this is how the water was released. No. So how is the approach of control the problems in with the water table? We have two approaches. We have the famous groundwater drawdown during excavation. We should put here some wells, and this is from these wells we are taking out the water. We can be in different stages. And then this is also how to consider this, we could say, the deformation after or during the water. Okay, this it is particularly interesting to have this number because this would be our control with the numerical analysis. Okay, this is a small summary. The important what this is what I told you about the earth pressure at the back of the wall and will rise while the pressure in front will decrease. This is important. This is a case 7 how we studied that that analysis of historic case retaining extraction under the groundwater table. This means that the effect of seepage has to be included directly in the design to achieve a safe design. And they stated that simplified calculation would lead to an adequate design. What does it mean? It doesn't mean that if we go back here, if we want to solve this problem only with relating with a weight problem, I mean the weight of this slab against the some pressure of the water, it it doesn't take into account the real behavior of the soil, and it can lead to a low cost effective design. In other words, our design is much over conservative, no? And this also is particularly attractive in those cases where the base slab or the thickness of the base slab is quite big. Okay. So this is exactly what I was telling. Regarding the groundwater, we have three possible conditions. One is neglected effector water table. We will not consider the effector water table. We know that there is a water table, but we will control it, or maybe the water table is not able to create any problems to our structure. Considering the effector water table only during a construction, because we have some sort of the watering, and then maybe for temporary structure is coupled with the watering. So for permanent, we will not use it, or permanent water table during construction and also long term. So this also can be considered in our design. Okay. The numerical solution. Regarding the numerical, the analytical solution, we have the most important formula is the DWALL, about the pressurization cone around the radial excavation, excavation or radial well, with some limitations. Always, these are always analytical solutions, so they start from some assumptions that are in some cases very strong. For example, the pre-formula consider that here we have an aqueduct. So the flow is the flow is basically horizontal. We do not have any vertical flow. So if we are working, for example, to study the watering with a flow, with a pumping, the DWALL formula should not be used. Should be used this curve, because it doesn't take into account this. Another option of analytical solution are the so-called flow nets. This particular is what I like, because they are very graphic, and they are based on the hydraulic gradient. So the main purpose of the flow net is to estimate the flow and to check if the impedance length of our pile is enough to cut the flow net, or to avoid a value of overflow, no? And this to calculate the flow net is the jumping from all the equipotential of the curvilinear shape to understand how many steps of hydraulic gradients I have to go through. Okay. Okay. After that is really, I would say, high-level introduction, because at the end of the day, everyone here knows about the groundwater. Go with the numerical solution. Clearly, we have three possibilities of approach towards the groundwater. One is this is on the left is how we should take into account the groundwater. The groundwater are the data of soil, and including the permeabilities, the conductivity, the void ratio, and whatever. Then we have the transmissivity between different nodes. If we have, for example, different layers, one layer of clay, which that is more impermeable with respect to some clay, and then we have the time if we wanted to carry out also a transient analysis, not depending of the time of the of the the flow. No? Clearly, we have a three approach. One is the model flow, is only calculating the flow. This can be done with a flow analysis. It can be done also in MIDAS and GTS. However, I do not suggest to use GTS only for flow analysis. There are other software would be easier. And one is the result of this model flow is the flow net. Then we have what we call the manual dewatering. The manual dewatering is the user is set up in, during each stage which levels are saturated with water and which levels are dry or semi-saturated. And this is interesting for solid structure interaction, in general for 3D analysis, for high-level analysis can be done. And the result of these are the internal forces due to impose the boundary condition, so the manual dewatering. And then we have the pure flow analysis. In flow analysis, we have two flow analysis. One is the transient, which is not the object of this webinar. And this is the steady state, which is I would say the flow analysis where the time is only used to measure the flow rate, not the increment of the decrement of the internal forces. Within the steady rate, we have also three options. At least MIDAS is offering us three options. In particular, MIDAS in this case is similar to Plaxis. No, so Plaxis we can do it. In FLAC we cannot. In FLAC we hardly have these two. Okay, the manual dewatering that it has not to be used, because if we are in steady state, doing the manual dewatering is mixing apples with oranges. So it's better to, if we want to carry out manual dewatering, it's better to do, I would say, classical stress analysis. Okay. And then within the coupled analysis, we have the coupled, where we have the first calculation is the flow, and the result of flow analysis are in terms of deformations, in terms of strains and tension, and these strains and tensions are mechanically implemented in the stiffness matrix of the mechanical model. I would say this is the pure and this is the best way of doing. And also MIDAS is offering the decoupled analysis, and these results are very attractive in those cases where the influence of the flow and the mechanical are not clearly clashes. In this case, the flow and mechanical are running parallel. For example, this case can be, for example, used in what we call the seepage analysis, for example, for a slope, a saturate slope, or, for example, if we are excavating, we are doing an excavation and we have a high water table, but we are dewatering quite far from the top of the water table. So this could be also resulting some sort of attractive. Okay. Okay. Let's go to the case study. The first case study is the MADRID tower. In MADRID, there are 4 towers. When here in MADRID, there was still a building market. They built 4 towers. I would say in the north of Madrid, close to Paseo La Castellana, which is in an ancient alluvium area. So they expecting some sort of water flow coming in this excavation. The excavation is of, as you can see, is for basement, and during the construction or during the review of the construction team, they proposed value engineering, changing the anchors here for pumps. Okay. So the excavation was done as was done previously with a temporary slopes in mid-ground. Then we have here a berm to install the walls, and then the construction of the excavation. So here they have some photos, and here you can see this is some level of water they are coming from some anchors. Nothing important. And here they are the monitoring of the stress of the anchors, because these anchors, as you can see, do not have the protection I show at the beginning regarding the water table, because they consider that here in this area we do not have a water table, but in this case they were monitoring the stress. No? So regarding the analysis in MIDAS, this is the analysis in MIDAS. These are the excavation I was telling you before. These are the dimensions of the model. The water approach, and this is a fully coupled analysis. What does it mean? Does it mean that, as you can see, how we can establish it in MIDAS? We have to, for each design, for each stage, we design an excavation. And this excavation has a nodal head. So this is doing fully coupled with manual dewatering. Okay. This because here the water level was not particularly important, and so we decided to do a coupled analysis. Okay, but with changing the manual dewatering. Okay, so this also was the duration, and as you can see, in order to speed up and to facilitate the possible numerical problems we could face, we set up the time. We set up the load factor with increment values of 33 stages. Okay, just to provide the stiffness matrix less by less, and to not to do any problem. These are the results of the struts between the various levels, just to check which levels of struts and which were our dimensions. And this is the solid pore stressor. As you can see here, we have a reduction of the pore stressor. Here also there were some ramps for facilitating the construction excavation. And here the equivalent flow net close to what we suppose were the drains. Okay. This was a simple way of modeling the water of the pore pressure. Another case is the excavation of the wall. This is an axisymmetric approach because it was a circular wall. It was 20 meters. And in this case, we carry out two analyses. One analysis, as you can see, I don't know if you can see here, is 0 seconds. So it's like without taking into account the time. And here is with 20 days, considering some sort of timing, no? Just to check the differences in terms of flow. Okay. These are the seepage, the total head. As you can see, is very is perfect. It's like from taking from a book the seepage, and here you also can see the two values depending of the difference time. Okay, here is 0 second, here is 20 days. As you can see, the value is the same. The value of pressure onto the structure is the same because the pressures and so the internal forces we are going to use to carry out our structural analysis do not depend on the time. What is depending on the time is evident is the flow. So as you can see here in 0 we have something for minus 5, and here we have a minus 0. So we have a 5 order of magnitude between the two calculations. This is helpful for us because sometimes as engineers they ask for a flow analysis, but when we have set up already the flow rate. So in this case, it's very easy to implement it in MIDAS because we can set up the day to have this flow rate, and we are sure that our pressure are not okay. This is okay. This is academic. This is the flow net at the end of the day, and how we could check against the numerical against the analytical solution. And then we have the case 3. This is a TBM launch chamber. It's another project we are involving in London. Here we have a shallow water table. In London we have the level table of the Thamesis, a very dense urban area. Then a complicated construction process, and then the interaction between these two partners. So 2 scenarios carry out. One scenario is the pure full, is the couple, and the one was coupled with the watering. I anticipated it because it's not working because of the difference of the potential energy we have in our excavation. We will go through later. Okay. So here, as you can see, the fully coupled analysis, we have all the phases in one stage set. Okay, so we are not going to define manually which type of pressure has some mesh set or some node. No. We tell MIDAS, this is your water table in this stage. It is the initial balance. And then less by less during excavation, we say, okay, right now your water table will be according to some position of drains. And we are going to have in this drain a flow of pumping, so negative, of I don't know, minus 1 liter per second or 2 liters per second, depending on what our hydrogeologist is telling us. No, and so as you can see here, we have a perfect the pressurization cone, and here also, as you can see, you have also vertical. You have also vertical flow because here is considering the flow net and the pumping. And here we here we have here there's some problem here sorry, is the problem here. So here, instead of the case with the manual calculation, where we are setting up manually we are setting up manually the pore pressure, and as you can see here, we have almost in pore pressure we have 391 kPa. So we have a lot of pore pressure. Okay, and this is going to create a yielding in this material, and there is a problem of convergence. Also, here, as you can see, this is the differences between the two levels, taking the same. This is the two approaches taken the same. At the end of the day, at the same step. No, here we have the perfect shape, and everything is working. And here you have these problems. Okay. And then we have also the something I would like also to underline here, that if I plot the vertical stresses, the vertical stresses here are the same value of the pore pressure. So basically, our ground is boiling. We are going to have heat, no? When in reality. So if I had to design this with manual dewatering, I tell, okay, this cannot be done. But in reality, with a good analysis, with a better and more refined analysis, and knowing how the GTS is working, we could create a very good analysis. No? Okay. Regarding the case 4 is also another elliptical shaft, and this is a shaft in the soil. This is an interface with tunneling, and here you can see the position of our drains. We have position out the element, and then we have position inside. Okay. Here, in this case, as you can see, also we have here a poor flow analysis. So we have only one tree from the stage set. So we do not have the changing manually. And as you can see here, you have two types of analysis. You have the analysis of the steady state, where you are analyzing only a flow analysis, and then you have the analysis of stresses, where you are taking into account the steady state analysis and implement in our MADRID. The results are the same. As you can see here, you have the vertical flow, and as you can see here, also there is a 3D effect, very difficult to capture with only a 2D analysis. No, here also you have a tunnel, so it is important also to define the watering in this area. Okay. Finally, as you can see, the watering was designed to discharge almost 200 kPa water pressure. So this is the initial phase, where we have our initial phase is minus 700 kPa of pore pressure, and this is the total, and we reached the 500. Okay, in order to excavate in without taking into account the sub pressure or the pressure of the water onto our slab. No? These are also the definition of the displacement. As you can see, the displacement is really small, but it's important also to manage the displacement. I don't know if you remind at the beginning, when I tell you about this displacement, this is one of the control we have to carry out after our flow analysis, because maybe the model can work, but our displacement are so high that can be invalidated by, I don't know, by the conditions we could have in here around. In this case, we are working in almost ground field conditions, apart some utilities. So we do not have much of major problems. Okay. Then, at the end of the day, what we are going to design is the structure. So here you have the forces and in the direction of SXX on the bottom and on the top. Because as you know, in MIDAS we have for each shell force we have three values: the top, which is the outer in this case, the down or the minimum, which is in the inner of the excavation. Then you have the average, no, depending on our depending of our calculation, we could choose one of the others. Okay. So the conclusions from what I show you, and if you want, we can go through the models. Water table, if present, can be neglected in some cases where engineer estimates that it does not affect the excavation and or the structural elements. No, this can be done in some cases. For example, in case one, I show you, we carry out a flow coupled analysis because we thought, or because the information we received was that was a water table, but then water table there did not appear, or appeared in very local cases, so was not a major problem, no? If water table is variable during the excavation, but it will be conducted a drainage onto the structure, it is possible to estimate it with analytical calculation or drawing a flow net. This is something that actually should be done should be done all the time. I mean, before going through the analysis, we should have a rough number, or more or less an idea of where we have to have our target level of water during each phase of excavation. No, however, as I pointed out at the beginning, the analytical solutions are very, very, very conservative. So if we could have a number that could be very, very conservative and not very then useful when we are going to implement it in our numerical models. In other cases, flow analysis must be considered. So now, how MIDAS GTS prescribes three main ways of simulating the water table. The manual imposition of the water table. This model can be employed with old models, more Coulomb, in soil. It is very quick, but it's not improvable in the watering process, because if we are changing manually something that has to be done in the time, we are going to risk to have numerical problems, because we are telling to our soil to pass from total or saturated conditions to drained conditions in one instant. And this can create instability, not only numerical instability, but also from physical point of view is not real. So our model would be not real, no? And then there is the decoupled analysis. In this case, flow and mechanical are solved in parallel, and it's quite good in very over-consolidating clay, for example, in some cases in London clay. And then the coupled analysis, in this case, flow before the mechanical. This is the typical, I mean, this is the typical approach. This is the most important. What I would like to underline here is that this free way of simulating the water table can be used in different options. The only thing is to take care of the soil model we are using. Personally, when, for example, I'm using Morpholomb or in Morpholomb for their coupled analysis, I experiment problems of convergence, and I have to improve the Morpholomb into I would say hyperbolic model like Arden soil or something else, because at the end of the day the yielding cap simulating the passage from saturated to unsaturated drainage is it is more acceptable from the program. Okay, we have a do the MIDAS, Damian, do the MIDAS GTS has the issue with small strain overshooting in HSS model? No, no. This also can be correct in your analysis control, in your simulation. For example, let me just check. I can open one case. For example, this one. Okay, so for example, here is the model we are mentioning. No, so if you come here in analysis, you have for example here in analysis control. You have here to work out with the small strain. Also, you can do it in your definition of the material. You come here, and in non-linear. Here you have the small strain parameters, which I do not use in this case, because in this case it's undrained behavior, and so we are considering without small strain. In this case, we do not have any issue. Actually, MIDAS allows you to define, comparing to other programs, for example, to Plaxis, the poor hardening soil, in which the small strain also depends on the dilatancy angle. So in this case, is much better, I would say. No. There is something I would like to mention, and it is the behavior of the permeability coefficient, the specific storativity. This I suggest you to use also the auto formulation. The formulation of storativity came in the manual in the part of the flow analysis, and not to calculate by hand. Because if you calculate by hand, you can have a problem, and I mean, it's based on my experience, and it costed me some time to to figure out why a model did not reach convergence. It was these parameters. Okay, what I was telling you is this. This is exactly how is the flow. Okay. So as you can see here, you have the excavation. They are completely steady state, but you have only one. I would say construction stage set. Okay. So for example, here you have this is a steady state. You see fully coupled stress seepage. So here we are calculating everything, and then you have all is fully coupled, and the flow is calculating here. Okay, so each time excavation 5 is directly recognized that excavation 5 and excavation 5 can be are the same, because I've defined it. Okay, so this is more or less what I would like to tell you. I don't know, Damian, if I answer to your question or if it's something not clear.